Okay, so just an announcement that I gave a couple extra days for turning in the lab. It was due this Friday, but I said we'll take it until Sunday. Okay, so you can use that time any way you so wish. And if you have questions, obviously you can post on Piazza or come by. Okay, there's somebody available every day of the week. If you arrange their office hours, today I have office hours, I think tomorrow and the day after, either one of the TAs or course assistants will have office hours. So you can see anyone any day of the week. Just don't expect to get instant response on weekends. Okay, weekdays we are always happy to help. All right, so let's. I'm sorry, what's the question?
The office hours are not there on the website for the TA and others. Only your office hours on the website.
Office hours have been posted on Piazza, but I will go update the website. I may have forgotten to reflect it. All of them were announced on Piazza. Okay, and we arranged it so that we have somebody available Monday through Friday. Okay, all right. So let's continue from where we left off last time, and if there is time at the end, I can see if you have questions about the lab that we can all answer in class as well. Okay, so last time we talked about RPCs and RMIs. We did lightweight RPCs. I talked about RMIs. Towards the end of the class, I talked about Sun RPCs. Today, I'm going to talk about a little more about message-oriented communication in terms of how we can classify these systems. So we talked about a whole bunch of them. We'll talk about a couple more today, but we want to think about how they actually work, based on their properties, how you can classify them. Okay, so that's one thing we'll do. And then later on in the class, we are going to talk about stream-oriented communication and video streaming, which uses a very different kind of communication than client-server or request-response style communication. Okay, so let's start with basically how to classify these systems. So what is shown here, this looks more complicated than it needs to be, but what is this picture is showing is two machines at two ends. This is a sender here and that's the receiver. Okay, and they are communicating. Okay, and they are communicating over a network, and this packet that goes out from the sender essentially traverses a sequence of routers along the way. Okay, until it gets to the destination. Each of these routers is responsible for deciding what is the next hop router to send the message to, so that it makes its way to the destination. Okay, so all the nodes in the middle here are responsible for routing. That's the sender and that's the receiver. This is the picture you want to keep in mind. Okay, now in the typical case, these routers that we have shown will be network routers. They are going to be using IP for routing. Okay. But as we will see that in today's class, you can also have what are called application level routers, okay, which essentially sit on an overlay network, and they also provide application level routing functionality. And we will see that in the context of message queuing systems, and also a little later on in the context of overlay network. But for now, all you need to keep in mind is we have sender, we have receiver. There is basically going to be routers along the way. Routers do hop by hop communication. Okay, and depending on the properties that these routers will provide to us, we'll actually get different kinds of communication systems. Okay, so let's talk a little bit about how to classify these communication systems into different categories. Okay, the first one is whether communication is persistent or it's not persistent, which means it's transient. Okay. Persistent communication is essentially also called store and forward delivery, where messages are actually stored at each hop for arbitrary periods of time before they're delivered to the next hop. Okay. The example which is actually taken from the book is not really communication example, but that is how post office delivers mail. Okay. You have mail, they sort it based on destination, and this is the old style delivery, not even what was done today, which was mail delivery by Pony Express, where you take the mail on a pony and you bring it to the next post office, where it sits for an arbitrary period of time before the pony that's serving the pair actually comes, picks it up and delivers it, and so on. So each hop here is like a router. The post office is like a router where it basically sorts incoming mail and basically queues it up to different outgoing destination, and it can be queued up for arbitrary periods of time. Okay? This is called persistent communication. Okay? The example from a systems perspective is that of email. Okay? When you send an email, there are mail routers along the way, SMTP servers, that actually are responsible for routing your email until it gets to the destination machine and the destination inbox. Okay? Now mail, if the destination machine is down, mail will actually be queued up at one of the intermediate mail servers for arbitrary periods of time, which means it is persistent. It's not discarded saying the machine destination is not up, so we are going to delete your email. It will be queued up for some period of time that's configurable. Okay? Case of mail servers typically keep it for 4 days. Yeah, now that can be configured arbitrarily. So your mail could be queued up for a long period of time until the destination node comes up and actually takes delivery, or the next hop comes up and takes delivery and continues to route it. Okay? So that's called persistent communication. As it turns out, nothing that we have studied in this sequence of lectures that preceded today's class actually does any persistent communication. But today we'll look at message queuing systems that actually offer persistent communication. It's not something we have done so far, but we are going to look at that today. Okay? So if your communication is not persistent, then it's transient. Okay? So transient communication also does hop by hop communication, but messages are not stored if the next hop is actually down for some reason. Message is immediately discarded. Okay? TCP/IP actually is transient communication. If your receiving host is down, or you establish a connection and one of the routers goes down, your packet will be discarded and you are going to get an error after some time. Or if you try to establish a connection to a machine that's down, you are going to get an error as well. Okay? So messages are essentially buffered in memory and they're only going to be sent to the next hop so long as the application or the next hop is up and executing. Otherwise the message is discarded. Okay? So the main difference between the two is in the persistent case, the queues that you have to store messages are going to persist. They are actually going to be disk-based queue where your message can be stored for arbitrary periods of time. In transient communication, the buffers are in memory. Okay, and then you can only store the message for short periods of time, and if you cannot connect to the next host and send the message onwards, you're going to discard it. Okay, so your communication could be persistent or transient, and transient communication, all of the TCP/IP based communication falls in this category. Okay, so everything we actually talked about so far happens to be transient. Okay, that's one dimension for classifying how messages are going to be sent. Okay, another dimension is whether communication is synchronous or asynchronous in nature. Okay, another way to think of this is synchronous communication, also called blocking communication. Asynchronous communication is non-blocking communication. Okay, so if your communication happens to be synchronous or blocking, what that means is the sender is going to block until the message is actually received by either the buffer, local buffer, remote buffer, or the application. You are going to block until you actually know what has happened to the message in terms of where you want it to be before you continue. So it's going to block in some way. Okay? In asynchronous communication, it's non-blocking. You're simply going to do a send, hand it off to your runtime, and then continue execution. Okay? You're not going to block at all. Okay? Yes, question.
Would you never have synchronous persistent communication?
Would you never have synchronous persistent communication? As we will see, every possible combination of these two dimensions is possible. Okay, so you have two dimensions, persistent, transient, synchronous or non-synchronous. So if you combine them, you are going to get at least 4, but we'll actually look at 6 combinations because some of them are variants. They will be persistent, synchronous, but you can get variants of them and so on. Okay, so let's go through this one at a time. Okay, so first one is persistent asynchronous communication, and I gave you an example being email. Persistent means you will store the messages for long periods of time. Asynchronous means non-blocking. Okay, you should realize that email is non-blocking. You don't sit in your mail client for your mail to be delivered to the recipient. You just send it and you can continue doing something else. Okay, so we will call that asynchronous. It doesn't block. Okay, so that's an example here. You will see that the A is a sender, B is a receiver. A sends the message, okay, and then because it's non-blocking, you continue execution immediately. Then the message makes its way, and this says there's an arbitrary delay until it gets to the destination because it's persistent. It can take a while for your message to actually get to the destination, and it might get stored there for some period of time before B takes delivery. That's when, in this case, email case, that's when B reads the message. Okay, the user at B reads the message. Okay, so that's persistent asynchronous. You can also have persistent synchronous, which means it's persistent but also blocking communication. Okay, in this case, what happens is A sends the message, but it will block. That's why there's a dotted line there. The message has to actually, in this case, get to B. You get an acknowledgement. So you'll block until you get an acknowledgement and continue. Okay, but because this is persistent, you are going to store that message at machine B. Okay, in this example, for an arbitrary period of time. Okay, so this could be the time between when it's received at B and when the application actually takes delivery could be arbitrary. Okay, because it's going to be stored. Okay, it's not in a memory buffer, it's stored in this case in a disk buffer, which means it's persistent buffer. Okay, we will come to some of this in a minute. Okay, now we have some other examples. So now we will look at transient communication. Okay, so we can have transient asynchronous, which is transient non-blocking communication. The best example of this is UDP. Okay, if you use UDP messages, okay, you're essentially going to do a send. UDP does not require acknowledgements unlike TCP, so you are going to immediately continue execution. Okay, and then so that's non-blocking. Okay, and because both TCP and UDP, they all run on IP, which is by definition transient in nature, your message is going to get there. However, if B is down, or so your message will be discarded at that point. Okay, so B has to be up and the application has to be executing for your message to be delivered successfully. Okay, that's the definition of what transient means in this case. Okay, so that's transient asynchronous, and then the last category is the transient synchronous communication, and we'll see there are several flavors of this, and most of what we talked about actually falls in that category. Okay, so here we have receipt based transient synchronous communication. Okay, so as I said, synchronous means blocking. Okay, blocking always means once you send, you are going to have to wait until an acknowledgement comes back. Okay, and transient essentially says that both the sender and receiver have to be executing for this to be successful. And the variant, there will be three variants of this. The variants depend on what the acknowledgement is telling you. Okay, receipt based transient synchronous simply says the acknowledgement tells me the message has been received at the receiver machine. Nothing beyond that. So all that has happened in this case, you'll see the message reached, you got an acknowledgement. So that's all that the ACK is telling you. It doesn't tell you whether the message was actually processed. Okay, so the processing will happen at some later time. So that's not what the acknowledgement will actually tell you. Okay, so that's receipt based. Okay, you can have delivery based transient synchronous communication. In this case, you are blocked until the message is received, and the acknowledgement only comes back once the message has actually been delivered to the application, not just is received at the OS. That is actually delivered to the application, and then you get an acknowledgement. Okay, asynchronous RPC is an example of this. Okay, basically your RPC goes, and once you received it, you get an acknowledgement. Okay, and then you have response based, so that's delivery based. Response based transient synchronous says, I am going to block until you message is received by the OS, received by the application, processed, and an reply comes back to you. Okay, that's actually RPC. That's what RPC does for us. That's an example of this, a simple RPC. So that's response based transient synchronous communication. Okay, so we'll see that there's every possible combination, and within the transient synchronous there are three variants. The variants simply differ in what the acknowledgement actually tells the sender in terms of what has happened. Okay, this is a classification of communication based systems. Okay, there are some things like streaming that's not in here, but any request response style protocol you can classify depending on its properties. Okay, I'll pause here to see if there are any questions on this. Yes?
In the previous slide, no, the previous
one. Oh, one. Okay.
Yeah, so in persistent synchronous communication,
yes.
After B starts and receives the message, why does A stop again?
Oh, question here is, in this example, actually that's true in many examples, after B starts, why does A stop? So A and B in this case, because it's persistent, there's no correlation between them. It is simply showing that when A is running, B is not running, and B is running, A may not have to run. But that is not necessary. It's simply saying there is no requirement. In transient, the requirement is A and B have to be actually executing. In this case, A and B execute at different points in time that may not have to overlap. They could overlap, but there's no requirement that they have to overlap. Okay? The same is true in this case of email. When you send the mail, you don't expect a receiver to be online and reading the mail. And similarly, when the receiver reads the email, there's no requirement that the sender is online at that time. Okay? Those two things are not coupled in time, so they could happen at arbitrary times. So say that's the same thing happening. Okay, it doesn't mean you have to stop running, it just says you don't have to run. Okay, any other questions here? Alright, so what I'm going to do is, we did the socket and all of this last time already, so I'm going to skip those slides, okay, and talk a little bit about, and we did MPI as well. Okay, and you will see, I just wanted to point out that MPI has these different flavors of send, which is B send, send, S send, and send receive, which actually map very well to these variants I talked about. Okay, so the variant here where you say that it has been received, that's receipt based, then there is a delivery based and there is a response based, and you will see that there are actually variants of send that do all of that. Okay, so in this case you say you basically wait until it's copied to remote buffer, S send says wait until receipt starts, send receive says send a message and wait for a reply. So those are the three variants. Actually they're all represented in different types of send commands in MPI, or send methods in MPI. Okay, all right. So now for the rest of the next 15-20 minutes, I'm going to talk about persistent communication, because everything we've done so far is transient communication. Okay? Persistent communication is something that you may not have encountered because they are part of this class of systems called message queuing systems. They are used in enterprise applications to build large-scale distributed applications of some sort. Okay, so what do? They essentially support some form of persistent communication. It could be synchronous or asynchronous, but there's intermediate storage of the message at arbitrary nodes, including the sender or the receiver. Okay, so essentially, if you will keep the message for an arbitrary period of time, this is why it's called store and forward. You will store it on disk for as long as you need to. When the next node becomes available, wants to take delivery, you will actually deliver. The same thing that happened in Pony Express mail, how mail was delivered. You will hold it at an intermediate post office for an arbitrary period of time before it can be sent on to the next hop. Okay, same is true in this case. Okay. The way this is going to work is we will assume that every node from the path, there's a path from the sender to the receiver, every node is going to have a queue or more than one queue. Okay. These queues are going to be persistent queues, which means they are disk queues, not queues that just sit in memory. Okay. And we are going to essentially build communication by inserting messages into queue or taking them from one queue and delivering it to the next queue. Okay. That's essentially how this whole thing is going to work. The only thing that the sender is going to be guaranteed in any persistent communication system is that the message will eventually get there. We don't know how long it is going to take because there will be arbitrary delays along each machine, okay, in the path. Unlike TCP/IP, where you basically communication takes place on the order of tens of milliseconds, here it can take hours or days before a message gets delivered. It's the same thing that actually happens in email. Okay? When you send a mail, there is no guarantee when the message will actually get delivered. Okay? Of course, if you make a mistake in the address, it may not get delivered at all, but assuming the address is valid, it can take an arbitrary period of time. That's how it is designed, because it's a store and forward type communication. Okay, so essentially it's loosely coupled, no guarantee when or if the message will actually get read. Okay. Here are the four scenarios, which goes back to the question that was asked, saying why had A stopped running. Okay. So essentially all of those four scenarios can be true during communication. The simplest scenario is sender sends a message, it goes into the queue, and the receiver is actually running at the same time, takes delivery of the message. Okay, both the sender and the receiver are actually executing when the communication takes place. This is always true in transient communication, but it's only one of four scenarios that can be true in persistent communication. That's the simplest case. Okay, here you have sender is running, inserts a message in the queue, the receiver is not running at this point, it will run later and take delivery. Okay? In particular, you will see in this case that the receiver is actually taking delivery of the message, but at this point the sender is no longer executing. Okay? And the fourth case is the sender has sent a message, they have stopped running, the message is just queued up in this persistent queue and the receiver is also not running, and the message will sit there in the queue for an arbitrary period of time. Okay, so all of those things can be true in message queuing system. In transient communication, only this scenario is true, otherwise you will actually get an error. Okay? Alright, so now here's a canonical more example of how message queuing systems work. Okay? So essentially there are two key methods, just as in socket communication you had send and receive. Okay, those were our two methods that we used for communication. In message queuing system you have put and get. Okay, put is going to insert a message into a queue. You say put, give a message like a buffer and a address of a queue. So it's going to just take that message and append it to the queue. Okay, so that's put. Get is going to actually pull a message from the queue and give you a message that's at the head of the queue. Okay, so those are our two canonical methods which will replace send and receive. Okay, and then there are some more here. Okay, you can actually poll a queue to see if some messages arrive. Okay, you don't have to do a block. If get is a blocking call. Okay, if it's basically going to block, if the queue is empty, it will block until a message comes and then give it to you. If you just want to check if the queue has a message, you can just do a poll saying is the queue empty or not. It just gives you a true or false reply saying is the queue empty or not empty. Okay? And then you can also have notify, which says if the message arrives, notify me, because you can have infrequent messages. You don't want to be blocked for long periods of time or poll frequently, so you can be asynchronously notified. So you have poll and notify that are two additional methods that you can have. And this picture essentially shows us what's going on. So here's a sender. The sender wants to send a message. Okay, so essentially it's going to get the address of the queue and then insert that message into the queue. Okay. Now this may not be the receiver. Typically you don't have a single hop. It might be an intermediate router and it goes to the queue of the router. That's going to essentially figure out what the next hop and extract the message, do another put and so on until it gets there. Okay, but in this case we have a simplified scenario where the sender is directly sending a message to the receiver without any intermediate router. Okay, so in this case the message will sit here in this queuing layer, okay, until the receiver takes delivery. Okay. This is often what's going to happen in email as well. Messages come and sit in your inbox until you start your mail client and take delivery and read your messages. Okay, the same is true in this case. Okay, any questions on this? Yes?
Is there ever a case where you take something off from the queue and the communication between like that buffer and the next one is, say, like not perfect until the message is lost?
Okay, question is there ever a scenario where you can actually take a message from the queue, but then there is some problem with the network and the message is lost? Okay? Of course, like in any communication medium, you have to do error control. Okay? TCP/IP does the same thing. It gets acknowledgements. If the acknowledgements don't come, you time out and you figure out whether you want to retransmit and so on. So you have to layer in any system, there will be failures. Network can get disconnected, machines can go down. If you want a reliable message queuing system, you have to deal with that error. Okay? So here we are not going to talk about error handling, but that's a given that there will be failures, and if you want reliability, you have to deal with all of those things. So that can certainly occur.
But that is happening at like a layer beneath. This layer is not going to like keep that message till it gets like an acknowledgement. Okay, so the question is that actually happening at the layer beneath? So this does not tell us how get, put, all of this actually is implemented. Okay, so if you want get to put to return a successful value, you want to make sure that not only has it reached there, but it's actually been inserted into the queue. You don't just say put and give it to the OS and return. Then if something goes wrong, you don't have a way to figure that. So that goes to the semantics of what put will do. Okay, if you essentially get a successful reply from put, if that success says that I actually got it to the other end, then that's what otherwise you will have to implement it internally by retransmitting and so on. Okay, any other questions here? Okay, so I'm going to show now a more complex variant of message queuing. So that was showing a simple example. Here you will see there's a sender.
Okay, you have a send queue, you have a receive queue. There are the application and there are other which are all part of a distributed system. Each of them has a send queue and a receive queue. Okay. In the receive queue, we'll have all the messages that are incoming. The send queue are the messages you want to send out. Okay, and any of these can send out a message to any of the other applications in the network. What is shown in the middle, which is R1, R2, R3, are routers. Okay, these are not network IP routers. These are message queuing routers. Okay, so they essentially have a set of queues as well. Okay, so they will get a message from another router or one of the endpoints, and then they will essentially route it to the next hop in the queue, in the path, and so on until it gets to the destination. Okay, so this routing is very similar to what happens in IP. With only one important difference: in a typical network router, those queues are memory queues. Your packets are only queued up and they go out immediately. In this case, the queues are persistent disk queues where messages can sit for arbitrary periods of time. And the endpoint queues, the send queues at each of the endpoints are also persistent queues. So that is why these are called persistent queuing systems. Okay, any questions on this? Okay, so now there are some, if you look at typical message queuing systems, you will see that they provide a lot of additional functionality in addition to the 4 methods I talked about. One of them is what is called a message broker. Okay. Message broker essentially is an application level program that provides additional functionality. Okay, so it can convert messages so that they can be understood by the destination. So you can do things like format conversions. They are also used in publish subscribe systems to figure out when to provide notifications and so on. So essentially, as the name broker suggests, it's an intermediary. Okay? It allows communication to happen by providing additional functionality. Okay? You can do translation of a message, you can do transformation of a message, and so on, so that the sender and receiver can communicate. You may be able to do protocol conversion and things like that. Okay, so essentially it's a proxy that's sitting between 2 routers, as you will see. So here you have this could be router 1 and router 2. Your queues are basically looked at by the broker. They do some transformation and then they send out the message. Okay, so you can do things like transcoding and so on. Yes, question?
Yeah, does the broker program work with encrypted messages?
Okay, question is, does the broker, or not does, can the broker work with encrypted messages? So if you have end-to-end encryption, okay, clearly a broker cannot transform an encrypted message. Okay, so the functionality of the broker depends on what you want to do and what the message has. If the message is encrypted, unless you decrypt it, you can't change the format. And if the encryption is end-to-end, you may not be able to decrypt it in the middle of the network. So in that case, what you can do will be limited. Okay. Any other questions? So I wanted to show one real world example. Okay, so WebSphere. So there are many message queuing systems. I don't know if anyone here has used any message queuing system. So there are open source ones called ZeroMQ or RabbitMQ. So these are all message queuing systems. They are used in publish subscribe systems as well. Okay, and then there are commercial message queuing systems. So this one is actually a product from IBM. So IBM has this thing called WebSphere. That's essentially a message queuing system. And you will see what it's a fairly complex distributed system middleware that provides persistent communication. So you're the sender, you're the receiver, and you will see that each hop is using RPC style communication to do get and put. Okay? Our get and put messages are essentially RPC messages that run between 2 nodes that are in the path from the sender to the receiver. So you could have a sender that takes a message and essentially calls the get RPC call, or rather the put RPC call, which is why you see a stub here, and then it goes to the next router and it gets inserted into a queue. And then you have these things called message channel agents, which are just doing some local processing where they will convert that message into a TCP packet or an RPC call and then send it to the next hop along the way and so on until you get it to the destination. Okay, so WebSphere provides you a set of functions and then it exposes APIs that are similar to get, put, notify and pull. And using that, you can write arbitrary distributed application. Okay, typically, this is used in publish subscribe like systems, where the message broker can keep track of when some data gets published, who has subscribed to it, and then you actually send it to whoever has subscribed to messages. That's one common use case, but there are many others. Okay, yes, question.
So in the previous slides, you have told that you have some sort of routers.
Yes.
So a message goes into a router, the router transmits it to another router, and so on.
Yes.
Okay. So how does the router know which router am I supposed to send a particular sort of message? Is that information local to that router, or do you have some sort of global information line?
Okay. So the question is, in message queuing system, there are intermediate routers that are going to route your messages. How does the router know where to send a particular message? Okay. So essentially, the routers have to implement a routing protocol, just as IP is a routing protocol. You can ask the same question in IP. How does IP know if I have a packet which has a destination IP address, what's the next router to send it to? Okay, because it has a routing table. The routing table tells it what to do based on. So you look up the source destination pairs or prefixes, and the routing table is going to tell you this is where you need to send it next. Okay. So same is true here. Okay. You are going to have an application level routing table, which means you will have some knowledge of the topology of your message queuing system, and you know, based on that topology and the destination address, you look up a routing table and say this is the next hop I need to send it to. Okay, so that's the same concept you are going to implement, but in the message queuing system.
Then where does the queue manager comes in?
Where does the queue manager? Are you talking about this one? So in the WebSphere MQ case, the question is what does the queue manager do? So what the queue manager is essentially doing is essentially looking up the routing table. So you'll see that there is a gray box here which is labeled that routing table. So the queue manager has essentially looked at the incoming message, and it has several destination queues. Okay? Each destination queue connects it to one of the routers that is in the next hop. Okay? So if let's say you have one router R1, okay, and it's connected to R2 and R3. Okay, you are going to have two queues here, an R2 queue and an R3 queue. Okay, and there is an incoming queue as well. Okay, so let's say a message comes in the incoming queue. Your queue manager is essentially performing the routing function. It's going to look at an incoming message. It's going to look at the routing table, and in this case, it has to make a one of two decisions. Should it be put in R2's queue or R3's queue? Because those are the only two choices you have. Okay, and then you are going to put it here or here. And then your, in this case, the MCAs are going to take that message and make a TCP/IP packet and send it to the next router, and it will go into the incoming queue there. The same thing will repeat until you get to the destination. Okay, that's how routing will be performed. Not unlike how network routers work. Any other questions? Okay, so we are going to switch gears. We are going to now. So we talked a little bit about persistent communication. It's something that you should know, even though most applications you tend to use transient communication. They'll use either sockets or RPCs or REST interfaces that you're implementing in your lab. All of those fall under transient communication. Okay, but there's a whole class of systems that provide persistent communication, hop by hop delivery, where each queue will keep the message for long periods of time. Okay, so something you should know if you haven't used them. Okay, so now we will switch gears and talk about a very different type of communication, which is stream-oriented communication, or essentially streaming. Okay, if you have audio streaming or video streaming, you are going to not use request-response paradigm. You are not using things like RPCs or client-server request-response communication. Your communication is going to be done very differently. Okay, it's basically being done using streaming. And there are many properties that you want to achieve when you do streaming over a network. Okay? The most important one is that timing is going to be crucial in stream-oriented communication. In request-response communication, we did not actually impose any time restrictions on if I send a request, I need to get a response in a certain amount of time, or the application will not function correct. Okay? So there was no such requirement. You could take arbitrary amounts of time. Okay? Typically, you don't want to take too long, otherwise the user might just think that the system has gone down. But you want to be responsive, but there is no deadline. Okay? On the other hand, in video streaming or audio streaming over a network, you essentially want data delivery to be done in a timely fashion. Okay? So let's say you go to YouTube and you start playing a video. Okay? Now once you started playing the video, the server has to keep sending more data to you until the whole video has been played out. And if you are at a certain point in the certain point in the video where you are playing something out, if you don't get the next piece of data, okay, in time, your playback is going to freeze. Okay, and you may have seen this problem that when you have occasionally, if your network is not performing well, okay, your YouTube playback seems jittery, or it will essentially keep freezing. Okay? The reason is that your network did not deliver the data in time, so there is no data to play. The next part of what you need to show, display to the user has not actually arrived over the network. Okay. So what this is saying is you want to also ensure in this case timely delivery, otherwise correctness is impacted, because a freeze in a video playback is actually incorrect playback of that video, okay, from our perspective. So if you have, let's say, 30 frames of video every second, okay, video can be encoded at different frame rates and different bit rates. Okay, if you say 30 frames a second, that means you have to deliver these 30 images every second to your video player from the server. Okay, if you don't get all of that data, then you will essentially have a video freeze, playback freeze. Okay. So timeliness is one important characteristic in video playback, and this is also called isochronous communication. Okay, essentially that means that you have some timeliness requirement. Okay, in addition to timeliness requirement, the other problem that you want to also reduce or avoid altogether is what is called jitter, which is the variation in the end-to-end packet delivery times. Okay, so essentially you want your packets that you are sending to have a delay bound. Okay, the only way you are going to guarantee correct delivery is you have a delay bound. So you send a packet, it's going to be received by this much time. If there is no delay bound, it may take a long time, and then you will have these problems. Okay? So you want to have a maximum bound on the delay, and jitter is the variation. If one packet takes 100 milliseconds, the next packet takes 150, the third packet says 50 milliseconds, the end-to-end delay is fluctuating on a packet by packet basis. That also causes problems, because there will be bigger gaps between some successive packets and small gaps between others. And I'm going to show you some pictures of this as well. And that will also cause problems in the playback, as we will see. Okay? So those are all important characteristics we want to keep in mind when we design a streaming protocol. Okay? The last but not least difference is that streaming typically works in push mode, not in pull mode. Okay? So you can hit play. Okay, so many streaming protocols, once as soon as you hit play, the server will keep sending you data. You don't say send me the next so much data so I can display it on my player or anything like that. The server will keep sending that data to you. Okay, so typically server push is the better mode. Having said that, most of the streaming protocols that you actually see in the internet today run over HTTP. Okay, HTTP is essentially a pull-based protocol. So we are using client pull to simulate push, even though server push is better suited. And the reason for this is HTTP is a standard protocol. Most players, browsers already know how to implement it. So they essentially use that protocol to implement push, even though push would have been a different protocol, that is push specific, would have been better. And many have been designed. None are actually used in practice. Although you will see lots and lots of research papers on different kinds of push protocol. What actually became popular was, let's just use HTTP to implement streaming, and I'll show how that is done as well. Okay, is that clear? So essentially push mode, trying to have bounds on your end-to-end delay and jitter, and ensuring timely delivery. Yeah, so any questions? Yes, no question.
This might be a dumb question, but what about media players that use Flash?
Okay, there's no dumb question, but what's the question?
Like, is it also the same thing there that it uses HTTP?
Okay, question is what about video players like use Flash? So in many cases, actually video players are capable of supporting multiple protocols. Okay, this doesn't mean a video player will support only one protocol, but the default that most of them end up using is essentially HTTP based streaming. It's called dash streaming. I'll talk about that in a little bit. Okay. But yeah, I mean, you could, and Flash has been around for a long time. All players in the early days, none of them used HTTP. They used other proprietary protocols. Okay, Windows Media Player had its own protocol, Real Player had its own protocol, and so on and so forth. Then they all switched to HTTP because that became the dominant mode by which you could deliver video without requiring any specific implementation. Okay. Okay. So now I wanted to talk about several different kinds of streaming. Video streaming can take two different types. Okay, you can have what's called live streaming and stored streaming. Live streaming is what happens when you use Skype, okay, or some other video conferencing or audio conferencing application. So essentially there's a camera and a microphone that's capturing whatever you're saying and whatever it's seeing live. It's encoding them, it's streaming it over a network, and you display it at the other end. So here is an example of a live streaming scenario where your camera, microphone, you're streaming and you display it at the other end. Okay? In this case, the requirements on end-to-end delay and all of that are very tight. Okay? Because the longer the delay, if you're having Skype conversation with someone, let's say you speak something, okay, and it takes one whole second for it to even be delivered, the other person will be seeing a silence in the middle. They won't know what's actually happening, and they might start talking thinking you're not speaking, and then all the communication gets messed up. Okay, so have good interactive live communication. Typically, studies have shown that end-to-end delay has to be 100-150 milliseconds. Anything longer you can perceive with your eyes or ears and feel like communication is not smooth. And then you might start seeing silence, and then you will start speaking over one another and so on. Okay? So that's an important requirement. Now, as opposed to live streaming, whenever you use things like YouTube or Netflix, you have what is called stored streaming, because whatever content is being streamed to you has already been generated and is stored on some disk somewhere. All that the server is doing is reading that file and sending it to you over a network. Okay? In this case, the video stream is being created live. Okay, there's an encoder that's going to take whatever your camera is capturing, convert that into a digital stream, a set of packets, and send it out. Okay, and then at the other end, it has to be decoded and displayed. Okay? So your live versus stored streaming, that's one analogy. And in live streaming, the requirements are tighter than stored streaming, because in stored streaming, it's one way. So there is essentially the server is just sending you files. So long as the file is playing out smoothly, you are happy. Okay? The end-to-end delay doesn't matter. The end-to-end delay only matters when you hit play and how long does it take for it to start playing. Sometimes it plays instantaneously, sometimes you will see something spinning, it may take a few seconds to play. Okay? That's only where the end-to-end delay matters. Beyond that, so long as your video plays smoothly, you don't care. Okay? So that's live versus stored. And then here is a third scenario, which is essentially where you're using streaming in a multicast mode. This is what happens when you have live telecast or webcast, where there's a sender, but lots of receivers are tuned into whatever this live event is. Okay, and then you're sending, and data is actually going through a distribution tree, and it receives a large set of receivers. Okay? So this is called multicast streaming or group based communication, where you are not only doing multicast, you are multicasting a video stream. Okay? This is a lot more complicated because your constant set of data, it is getting distributed through these intermediate nodes are actually routers, and these things are essentially all the receivers whoever have tuned into whatever the live broadcast is and so on. Okay, so if you view a live sports event, okay, over the internet, you essentially some sort of a distribution tree that is delivering all the content from one source, which is the server where it's being sent out to a large number of receivers. Okay? So that's the third type of streaming. In the first two, you have one-to-one communication, one sender and one receiver. In this case, you have one sender that's sending the data to lots of receivers. Okay, so now with that background, let's talk a little bit about what are the properties you want on your video or audio streaming protocol. Okay? Now, because you have things like timeliness requirements, some notion of putting a bound on the maximum end-to-end delay and so on, okay, you want the network to give you certain properties in order for your video streaming to work well. Okay? We will refer to what properties we want from our network as this term quality of service. That's the service quality we want from our network. If this network cannot deliver us that minimum service quality, our playback is going to suffer. Okay? So how you specify this service quality, or this term quality of service also has an acronym called QoS. Okay? If you hear the term QoS, you should know it means quality of service. So what you're saying is you are going to specify some metrics saying, I would like this kind of performance from this network in order for this to work well. Okay? The simplest quality of service metric is bandwidth. Okay? If you have, let's say, HD quality video, you're doing, let's say, Netflix or YouTube, but watching HD quality stream. Okay? And let's say that's encoded at 1 megabit per second. If your network gives you half a megabit bandwidth max, there's no way you're going to play back 1 megabit per second video and have a smooth playback. Okay? So the most simple QoS requirement is simply saying this video is encoded at this rate, this bandwidth, so you need at least that much bandwidth. If your network is not capable of giving you that, then it's not going to work. Okay? But there are many others, as we will see. Okay, so that the first one, the bandwidth, is also called the bit rate. That's the rate at which the video was encoded, but you can say I need a delay bound, I need the end-to-end delay to be specified, the maximum jitter to be specified, etc. Okay, so there could be a large number of requirements you could impose on the network. And here's an example of what the data looks like, and to have to stream a data that has these kinds of needs, what kind of service quality are you requiring from the network? Okay? So an important thing here that you will see, okay, which I did not mention, is a bound on the loss. Okay? So another important implication of having a timeliness requirement is that you often don't have time to retransmit the data. Okay? You could use TCP. Okay, TCP, if your data does not make it to the other end, TCP can buffer and retransmit. But getting late data is as good as getting no data because it did not arrive on time. Okay, if you already reached a point and TCP is still waiting for a timeout to retransmit some packets that were lost by the network, it still does not give you adequate performance. So lower loss rate is important, because the more loss you have, the more retransmissions you are going to require. The more retransmissions mean more data is going to arrive later than usual. Yeah, because the original packet did not get there on time. Now the retransmission of that packet is going to arrive even later. And late data means you are going to have playback glitches and whatnot. Okay? So in many cases you want two properties, which is at least a minimum bandwidth and at least a minimum maximum loss rate, which is low. Okay, so if you can get those two things from your network, in most cases you should be okay. But typically you would want more than those two. But those are two very basic service quality requirements you would want from your network. Okay? And you will see here there are many other things like maximum delay variation, maximum delay, and so on. So you could ask the network, I would like all of these characteristics for me to stream it. Okay? Now, having said all of this, you should realize that the internet gives you no guarantee at all. Okay, so you could certainly ask, but if you have a best effort network such as the internet, it's not going to give you these guarantees. There were other networks that were designed where you could specifically request saying, I am going to stream a 1 megabit per second video and I need at least that much bandwidth, and I need a loss rate that's less than 1 packet every 1,000 packets, or you could specify those requirements. The network would then go and reserve enough resources to guarantee you those things. Okay? But those kinds of networks are not prevalent in today's networks. Internet has grown as a best effort network, and that's the way it is. Okay? So despite your data needing certain inherent quality requirements from the network, you still have to use a best effort network to deliver it, which makes it even more challenging, because you can never guarantee anything to the user. You can only make the best effort to give as good performance as possible. This is why today, even today, you will see playback glitches because internet does not guarantee you a minimum bit rate or a delay or a loss rate or any of those things. Okay, you still have to deal with that in some other way. Is that clear? Okay. Yes, question.
So, for example, YouTube is serving the video content. I've seen that even if the video is long, for like 1 hour long, it will only give you some chunk of that video, say 15 minutes of that video. So that one request which started from the client is not serving the whole content. So is there like multiple requests, like after reaching 10 minutes of the video, it makes another request and gets some more data?
Okay, the question is how is the client actually requesting data from the server when you're trying to play a video file? Okay, and there are two, depending on whether you are going to use a server push protocol or a simple HTTP based client pull, which is what is actually done. The answer is going to differ. Okay, I'm going to draw a picture here. Okay, so let's say you have a client. Okay, that's your browser and that's your video, whatever it is, and then here is your server. Okay, if you have a simple push based protocol, the way they work is when as soon as you hit the play button on some video, a play request goes to the server. Okay, beyond that, the client is not going to make any more requests. All that is going to do is it's going to listen on a socket, and the server is going to push a steady amount of data on the network, and it keeps arriving. You just keep listening, grab that data, and start playing it out. Okay, there are no requests made at all. That's how server push is going to work. Okay, so this is push. Okay, if you have client pull, okay, you can essentially do. Okay, so what is going to happen is you will have play, but then you will make a request saying give me one chunk. And it's going to be HTTP request. One chunk is going to come back. That's going to give you a few, maybe some 1 second of playback or a few seconds of playback. Okay, and as that chunk is being played out, your player actually has to make the next request. Give me the next chunk. Give me chunk 2. Then you will get another chunk, and then you will ask for chunk 3. So this is what is going to happen in the HTTP case. Okay, depending on the size of the chunk, you have some amount of time to retrieve the next chunk. If that next data does not arrive and you already started playing this chunk, then you are going to get a playback glitch. So you have to be much more careful in this case to ensure that you can parallelize the playing of the video while you're requesting the next part or the next chunk in the video and so on. And we'll talk about how this works in the context of HTTP in just a little bit. Okay. Now, in neither of these two cases, if the network is the internet, can you actually tell the network saying I need 1 megabit or I need such and such delay bounds and or such and such loss rate or anything like that? Okay, if let's say as you're streaming, one of these chunks gets lost, okay, if there is no time to retransmit once you start playing it out, okay, you will have very limited room to, you could if you buffer a little bit, but there is very limited time. So you want low loss rates as well for good performance. Okay. So I'm going to take one technique from this service quality or QoS requirement and explain to you how you can specify this in some detail and how the network can actually ensure, or in this case it will be the OS, how it can even ensure that service quality. Okay, there are many ways that you could have asked for these properties or service quality from the network, and this network can actually guarantee you that. Although the internet does not do that, it's instructive to at least understand how you could have possibly done it from a research perspective. Okay, so the one that we are going to look at is actually going to be how to guarantee some bandwidth, okay, or and so on. So there is a technique called rate regulation or token bucket that allows you to specify, okay, a requirement that says make sure that this data goes out at a certain bandwidth rate R, and you allow some variation in R, which is going to be governed by a parameter called the burstiness parameter, which is how much can you deviate from R for some short periods of time. Okay, so token bucket essentially has two parameters, a rate parameter and a burstiness parameter, and I'm going to draw a picture here to explain how that works. Okay. So the client can say, guarantee to me that any data I sent can be sent at a rate r with a burstiness of b. Okay? So rate r, so if the burstiness is actually set to 1, then this becomes a constant rate data transfer. I'm going to send it at a constant rate of r. There's no deviation allowed from it. Okay? Any burstiness that's greater than 1, let's say I've put a burstiness of 10, says I can actually B, in this case if B is in units of packets, that says I can send B packets at a time instantaneously. That will exceed the rate, steady rate R. Okay, but I can actually, that puts a limit on how much I'm allowed to deviate from the steady rate R. Okay? So those are the two packets, or rather parameters of a token bucket, and essentially what the token bucket regulator does, if you draw this property in terms of a graph, the x-axis is time and the y-axis is packets sent. Okay, the packets that you can send at by any time t is going to be bounded by this line, which is essentially has a slope of r and a y-intercept of b. Okay, this is what the token bucket will allow you or guarantee to you. So it says that at any time t, let's say at this time t, the amount of packets you would have sent cannot exceed r times t plus b. Because if you can send at a steady rate r, then in time t you could have sent r times t packets. Yeah, r is the packet rate that you asked for. Okay, so that's the maximum amount of packets you can send, and since your burstiness is b, you could have sent an additional b packets beyond the steady rate. That's how much you can deviate. That's the upper bound on how much data you can send in any time. Okay, how to implement this I'll show you. That's what that picture is showing you. But the property of a token bucket rate regulator, okay, is that if it has two parameters, a rate parameter and a burstiness parameter, and it guarantees to you that at any time t, the amount of data that the sender can send cannot exceed this property. Okay, r times t plus b. Yes, question.
Why is the burstiness important?
Why is the burstiness important? That's a good question. So let me explain why the burstiness is even matters. Okay. Now, if you actually look at how audio or video data is encoded, okay, you will see that there is an average rate, let's say it's 1 megabit per second, but that's not the rate, that's not the amount of data that's present in every frame. Okay, because you are using things like JPEG and MPEG compression, the amount of compression that you get out of every image is variable. Okay, so if you have, let's say, if you're encoding a video and if the video is completely still pictures, there's no movement in the video, you are going to get very good compression because you can actually say this picture looks like that picture. That can be encoded in short amount of. But let's say it's an image of some sports scene where there's a lot of movement. Okay, so there is some person here, the person moves here, person moves somewhere else, and so on. Okay, you have to now encode a lot more information in your video. What that means is the size, the compressed size of each of these images is actually going to be higher. In fact, it will vary over time depending on the complexity of the picture. Okay? So what this also says is if you actually use an encoder like MPEG or some such thing, the data that you have will not be of a constant rate because the compression will vary from one image to another. So you cannot say if I have 1 megabit per second video, every image in 1 second, the images are exactly 1 megabit. They will fluctuate over time. So you want to now figure out what the property of this video stream is, which means you want to deviate. So you will say, I need a 1 megabit channel to send my data. But I want a burstiness parameter that allows me to send larger frames if the frames are not compressed as much. Okay, so you can actually send more than the steady average rate. So that's where it actually helps. So is that clear? Yes, no question.
Most modern players are like adaptive to the bandwidth available. So has it got to do something with R&B?
Okay, question is most players are adaptive to the bandwidth. So we'll talk about most players, what they do today. The bandwidth of the network can fluctuate over time. This is not saying that. This is simply saying what is the client allowed to send. Okay? What happens when the data goes on the network is not what is being done here. Okay, so it's simply saying client says I need to send data at a rate R, but I need the ability to send more than the rate R, and how much more is governed by the burst parameter. The larger the burst, the more data you can send, which means instantaneous rate can exceed R by larger and larger amounts. Okay, yes.
Does this also need you to know what you are going to transmit on your channel? So if you want to say B, then
Yes. The question is, does it need you to know what you are going to send? It absolutely needs you to know the characteristics of the data. If you have a stored video file, that's easy because you can analyze it and say these are the properties of the file. If you are generating live video, this is going to be hard to achieve. Okay, your question.
So is the R dependent on the protocol or the type of video? Or like, is it a case-to-case basis or the same?
Okay, so question is, what does R depend on? Its type of video or whatnot? So this is an abstract concept. This is just saying R packets per second, and I'm allowed to send at any one time a burst of B packets instantaneously. How you determine R is going to depend on what you're using it for. If it's video file, you'll have to analyze it and get translate that whatever the properties of the file are into R.
Because in the sports example which you have given, the rate will be higher every time, right? So it's like a constant R, like the number of the data which you need to send is high every time, so there won't be any variation.
Okay, question is, if in the sports example there's a lot of motion, it's going to be high every time. You have to realize that even if it's a sports event and there's a lot of motion, the motion may change over time, depending on what is it that the sports event is showing. If we're showing scenes of spectators, there's no motion. If we're showing the player, there may be motion. So even within a video, this is going to fluctuate over time. Same is true of a movie. Right? If you have a movie, there may be an action scene and there may be some other scene, and there's the motion complexity will vary and the encoding rate will vary. So that is not something you can figure out ahead of time. Okay? All right, so now let me talk about how you actually can enforce this property. That is actually done by the token bucket. Okay, so you say, here's an application, let's say it's a streaming application. It says, I am going to send data at a steady rate R. At any time I want to send, be able to send a burst of up to B packets at some time. Okay. You specify that. The OS will then create us, let's say in this case, a special type of socket for you that is going to enforce that property. And it is enforced using this notion of a token bucket. It's also called a leaky bucket. Okay. And the rule is, before every packet is sent, it has to grab a token. Okay. If there is no token available, it has to wait for a token to become available. Okay. So we will basically fill up a bucket with B tokens when you start. Okay. When you start, you have a bucket that has B token. And then we will steadily generate tokens at a rate of R tokens a second. So we'll keep adding R tokens into this bucket every second. Okay. The depth of your bucket is going to be B. If your bucket is full of B tokens, you cannot generate any more tokens, or basically it's overflowing, so you can't add more tokens. Okay. Your bucket can hold at most B tokens, or it has a capacity of B. Okay. It will start it with the bucket being full, which means it starts with B tokens. And then you'll keep generating R tokens every second. If the bucket is not full, you'll keep adding to R tokens. And if it fills up, you can keep generating tokens, but they can't be added. Okay. Okay, so that's how you are going to have this bucket, and every time a packet is generated by the network, you do a send, you have to look in the bucket and grab a token. If you get a token, you get to be transmitted. If you don't have a token, then you have to wait. Okay. So that's the rule we are going to use to decide how to send data. Okay. So now you can think of what is going to happen. So your application, when it starts up, it can instantaneously generate B packets. They can all go out because there are B tokens. They can all grab one token each, and they can all be sent immediately without waiting at all. Okay. At this point, the token bucket is going to become empty because all the B tokens have been taken. Okay. And now you are steadily generating R tokens a second, so you'll keep adding R tokens every second. So at this point on, okay, because you are only generating R tokens a second, you are limited to actually sending at R packets a second as well, because that's the rate at which you're generating tokens. And if you generate packets at a faster rate, you will basically empty the bucket and have to wait. Okay, every 1 over R seconds, you're going to generate another token. So if you generate a packet, there's no token, it has to wait at most 1 over R. Okay, the next token gets generated, you can go out. Okay. So in this case, what the trivial example I just gave you, initially you sent B packets. Okay. And then from this point, you're essentially sending at a rate of R. So you're still bounded by RT plus B. Okay. But you don't have to do that. Let's say initially you don't do anything. You're simply generating at a rate of R. So you generate at a rate of R. Each of these things go out at a rate of R. So your sending rate is going to look like this. Slope is R times T, but you're not actually use the burst at all. You send at a constant rate of. But at any point, you can actually send at a faster rate by sending more packets, because you have up to B, you can instantaneously send B. So you can actually do this, but you'll always be bounded by this upper line, which tells us that that's the amount of packets you could have sent at any given time. Okay, so that's how your OS is going to implement. Okay, there's no real bucket in the OS, that's an abstraction. You have to realize that. But it's basically called a leaky bucket because it's leaking tokens at a rate of R. Okay, and then the depth of your bucket is B. Okay, and then the idea is that whenever a bucket leaks a token, a packet can go out at that time. That is why it's called a leaky bucket or a token bucket regulator. Okay, it's an OS mechanism. There are many operating systems where you can essentially specify an upper bound on how much data you can transmit. Okay, so you can say, here's an application, I want to bound its rate to some amount, and that is what it's going to get. That's how you can use it. Okay, now most applications will not use this. Where it actually gets used are things like virtual machines. Okay, you create a VM. Okay, you can, if you look in the configuration options, you can actually bound the amount of network bandwidth that's allocated to that VM. The way the OS will actually bound the bandwidth is internally it will associate a rate regulator or a token regulator with that VM, which will prevent it from sending more than the bandwidth you allocated to it. So this is a way to bound how much data you can send out at any given time. Okay, so those are scenarios where these things get used, not in streaming. They're actually more popular in things like VMs. Any questions? Question.
So over here, this is like saying how much can this application send out. It's not saying anything about how much the receiver will get, right?
Yes, good point. This is only going to do what is called policing at the sender. Okay, to actually have end-to-end QoS, you have to guarantee many things. You have to make sure that the sender is well behaved. This is ensuring that the sender is well behaved, is not sending at a rate of more than R. You want to also ensure that the network is well behaved, that you are sending at a steady rate of R. You want the network to deliver all of those packets with minimum loss by bounding the delay and so on. So those parts we have not talked about. Okay, I'm just giving you a simple glimpse of how you can go about implementing quality of service. The network part is more challenging, and in any case, internet doesn't do it for us. Okay? But this one, even though it was designed for things like streaming, is actually used. Virtualization technology uses it. For example, if you have 5 VMs, you can take your 1 gigabit Ethernet and say this VM gets 100 megabits out of that 1. How do you enforce it? You have to use something like this to say that that VM can never use more than 100 megabits per second of my gigabit network. Okay? You are going to put a rate regulator to ensure that. Any other questions here? Okay, so that is essentially end-to-end, or not end-to-end, rather quality of service at the sender. But there are many other things you want to be able to ensure. And when this was an active area of research, this was more than 20 years ago, people designed alternatives to TCP/IP protocol, which was all best effort. So they said, okay, the network routers need to provide guarantees. How are you going to guarantee loss rate? If you are, before you drop a packet during times of congestion, you want to ensure that the amount of packets dropped for any given connection is limited by the loss rate you're guaranteed to it. So if you say, I guarantee your loss rate of X, if there is network congestion, you can at most drop that many packets. So you have to be aware of what has been promised to every flow, want to enforce it and so on. That makes the network architecture a lot more complicated. You're starting to put more and more state in the network, because you have to keep state of what has been promised to every flow and enforce that during problem time like congestion and other things. Okay, and that does not scale, which is why none of those techniques, although they were good techniques, never actually made it into real routers. Okay? And routers continue to be best effort. Best effort is I don't guarantee anything at all. I'm going to do whatever I possibly can, and that's all I can guarantee. Not really guarantee, but give to the application. Okay? So best effort networks basically are simpler in terms of network architecture, because they don't have to implement these additional functions in order to enforce QoS. Enforcing QoS essentially complicates network design. And you will see there were lots of these techniques that were proposed at one point or the other. Okay. Now, although this is not deployed in the broader internet, some small variants of these ideas have been actually being deployed inside data centers. Okay, because you want to again guarantee properties to applications in data centers, and there are high volume applications and so on. So in the context of data center networks, a few of these ideas have started re-emerging. Whether they will become popular or not, and we'll see, only time will tell, but you will see now again papers that have some of these ideas. Okay, so that's how research goes. You come up with some good idea, and you write a lot of papers, it becomes commercial failure, then you do something else, then you come up with some variant of the idea and so on. Okay. All right, so now let me show you, because the internet is a best effort medium, you can't guarantee loss, you can't guarantee end-to-end delay and so on. How is it that you can still give good performance to your end users? Okay. What do client players actually do? Okay, and here's an example that tells us one technique that can be used, which is essentially we are going to use client-side buffering to try to get over some of this problem. And this picture tells us what kinds of problems we should expect. Okay, so this is the timeline, x-axis. Okay. What is at the top is how the sender is sending packets. Okay, this is a set of video packets that are being sent. Okay, you will see the sender is sending them at a steady rate, 1, 2, 3, and they are equally spaced. So if this is 30 frames a second, you can assume that I send 30 packets a second. I'm assuming that one packet is 1 frame, which is not true, but it's a simplification. Okay. So let's say you send 30 packets a second, which means every 33 milliseconds you'll send a packet. Okay. So you're sending them at some steady rate. Now, for it to get to the destination, there's going to be a delay. Okay, so the packet 1 actually arrives at this point in time. Okay, so it has seen some delay to propagate. Packet 2 sees a bigger delay. Okay, so it arrives at this point in time. Packet 3 also sees a large delay, so it arrives. So you see the spacing is increased. Then packets 4, 5 see a smaller delay. Okay, so they arrive actually fairly close to 3 and 4, and then 6 sees a bigger delay, 7 sees a bigger delay. So you are going to see an arbitrary delay that keeps fluctuating because it's a best effort delivery. Okay, depending on how much congestion you see in the network, you will see arbitrary amounts of queuing. The delays are caused by queues in the network. If a packet arrives in a network, it's going to be queued up. There are other packets ahead of it. They have to be sent before your packet gets sent. So you will see a longer delay in that router. Okay, if there's no congestion, your packet comes in, it will go out immediately to the next hop. Okay, so the state of the network will cause variation in the delay. Yeah. Now the problem is, if you start playing the video as soon as you see the first packet, you are going to see a problem, because the video is encoded at 30 packets a second. So you'll start playing the first packet, 33 milliseconds later you expect the next packet, which is not arrived. Okay, it's actually arriving much later than that, because 33 milliseconds is that gap, that's the rate at which you send. So you had expected the packet to come fairly close to packet 1, it doesn't arrive, so you will see a glitch. Okay, so then you will wait. Then if you start playing the second packet, then you will again see a glitch. Okay, because third packet has an error. Then 3, 4, 5 will play out smoothly. Then you will see another glitch and so on. Okay? So if you simply start playing your data as soon as it arrives on the network, you will get very bad user performance, because there will be frequent glitches. So the question is, what could you do? Okay? What most of these client players do is they don't start playing data as soon as the packet comes. They will start buffering. Okay? And then you buffer some amount of data, and then you start playing it out. Okay, so in this case, what is shown is, this is how it has been received by the player, but the player says, I'm going to buffer 6 packets before I start playing. So you hit play, you wait for so much data to arrive, then you start playing it out. So now you start playing out 1, 2, 3, 4, 5, 33 milliseconds apart. You played out 7, okay? You emptied your buffer, because after 7, no data has arrived. Okay? And then you see a glitch at this point, okay? Because 8 is actually not yet arrived. So you will see a glitch. You will want to probably pause for a long period of time, buffer some more, and then start playing out again. So what this shows is even 6 packets is not enough, because we basically emptied our buffer and the delays are long enough that you basically should have probably buffered for longer. Okay? So the worse your network performance, the longer you should buffer in order for you to get smooth playback. If you have enough data in your buffer, you can start playing it out and essentially mask the problems in the network. That is what it's trying to show. Is that clear? Okay. So now the clients are adaptive in terms of how much you can buffer. The worst case, you buffer until the entire video has been delivered to you. Then there is guarantee that no playback glitch, but you probably will wait 2 hours before you play your movie. Okay, that's not good. Okay, so users will not want to wait too long. As soon as you hit play, user expects the video to start. But the player cannot start, because if it starts too soon, he will basically give worse performance. So there is a lot of work in how long should you wait so the user does not get impatient, yet you build up enough buffer to mask all these problems. Okay? The shorter you make the user wait, the better they feel that the network is doing for them, because you will see video started playing. Okay? But if you do start playing too soon, you will have buffer underrun, so 10 seconds later you will immediately see a glitch. Then your user becomes unhappy. Okay? So buffering enough is an interesting problem, and in the internet you don't know ahead of time. Because the best effort net, it doesn't tell you this is the bound. If I knew the bound on the end-to-end delay, I could actually derive how much I need to buffer. But you don't know, because the delay keeps varying, so you are going to have all sorts of problems. And this is why you will see if there is a glitch, you will see a message saying client buffering. What your client has done is saying 6 is not enough, so now I'm going to make it 10 packets. So I'll wait until 10 more packets show up and buffer, and eventually you will find the right balance after 1 or 2 attempts. Okay, so that's how you can do adaptive buffering and so on. Okay, so I'm going to see if I have. Okay, so I think we ran out of time, so let's just stop here today. Next Monday I'll continue some of this discussion.